The purpose of this video is to go over the working of a problem that I usually give my students on solving a problem involving a one sample t-test, starting with a basic word problem, giving you some data, and then having you go through the process. Now, one of the things you need to understand is that there is a process associated with this, and the process starts at the very beginning with just calculating some basic numbers that you're going to need. Sigma x's and x minus x bars, all those basic numbers that you're going to need to calculate to ultimately work the problem. Then the next step is to come up with all the descriptive statistics. And if you recall, descriptive statistics are those that are used to describe a set of data or a population. So in this case, we're going to come up with the mean, x bar, standard deviation, whatever mu is, the mu that is given to you in the problem for the population mean that you're going to compare to x bar, and the standard error of the mean, which is our estimate of the variance of the population mean, mu. So you crank those out, you figure out what those are, and then the next step is to identify what the dependent variable is. The dependent variable is going to be the thing that was counted, so you got to figure out what that is, and you need to tell me what was counted and what the range of scores were, and then give me some idea of what that range of scores are, high, medium, low. After that, you need to figure out what the alpha value is. In these problems, it's either going to be 0.05 or 0.01. And from all of that information, you're going to be able to come up with the null and alternative hypotheses. And that's really the center point of all of this. That's why I have stars around it here. The null and alternative hypotheses are going to basically tell you what you're testing, right? They're going to be telling you what you're going to be deciding. Are you going to be deciding that your sample mean is significantly different from the population mean that's given to you? If that's the case, you reject the null hypothesis. Or are you going to decide that the sample mean and the population mean that's given to you, that they're the same, that there's no significant difference between the two? In that case, you will fail to reject the null hypothesis. So it's at this part here where you have to tell me what the null hypothesis is, and of course what the alternative hypothesis is, which is the opposite of the null hypothesis, and write those out. Based on all that information, you're going to be telling me what inferential test you're going to be using. Now, you only know one. You only know one inferential test at the moment, and that is the one sample t-test. So what you're going to write here as an answer for this part of the test question is one sample t-test. After you tell me what inferential test you're going to use based on all this knowledge, you're going to calculate the obtained t-value. So you're going to go and use the formula to calculate the obtained t, and you're going to use all these numbers that you calculated ahead of time up on the top. Once you've calculated that obtained t-value, you have to compare it to something to make a decision. And what you're going to compare it to is the critical t-value, which you're going to find in the table in the back of your book. Using the alpha level, the degrees of freedom, and whether it's a one-tailed versus two-tailed test, you're going to find the appropriate critical t. And then you're going to compare the critical t value that you got in the back of the book to that you calculated. And you're going to then make a decision. If the value that you calculated from the data is bigger than the value that you got out of the back of the book for the critical t, then you reject the null hypothesis. Since you reject the null hypothesis, what does that leave you with? That leaves you with the alternative hypothesis that, in fact, there is a significant difference between these two numbers, between the mean of my data and the mu that I was given representing the population mean. If, on the other hand, you calculate a t and it's smaller or equal to the critical t that you got in the back of the book, that means you fail to reject the null hypothesis, which means you can't reject it, you have to keep it, you have to retain it, meaning that there is no significant difference between the mean of your sample data and the mu that was given to you to compare it to. After you've decided whether to reject or fail to reject the null hypothesis, that's going to, of course, guide you to what you conclude about the data. And what you're going to conclude about the data is you're going to draw a conclusion that is based upon a comparison of the X bar for your data and the mu for your population. So you're going to say something like, there is a significant difference between the sample from this experiment and the population mean that was given. All right, so that's the process. And the reason it's really hard to, it's impossible to come up with one process that works every time, all the time, everywhere. Because for each one of these steps, for each one of the circles in this process, there's 5 different ways of doing it. And different people have different things they like to do. So you're going to encounter lots of different ways of doing these things. But this is the method that I've chosen to teach you. It's pretty straightforward, and it leads you to a conclusion based on the data. So let's now go ahead and take a look at the problem. All right, so let's take a look at our problem now. A social psychologist wanted to test the hypothesis that male students at her university are different in facial attractiveness than the students at other universities. According to one paper, the average facial attractiveness of male college students in the U.S., which is going to be the number mu that you're going to use, as rated by females, is 5.1 on a scale of 1 to 10, where a score of 10 is maximum attractiveness. So the social psychologist conducts a small study. She takes photos of 8, that should be an 8, not a 6, my apologies. She takes photos of 8 male students at her university. The 8 target photos are then rated by 120 female students who score each of them on a scale of 1 to 10, where a score of 10 is maximum attractiveness. Okay. For each of the 6 target photos, 120 ratings are averaged to come up with one attractiveness score for each of the 8 target photos. The average facial attractiveness scores for each of the 8 target photos are recorded in the table below. Use the X bar and X minus X bar columns to record the differences for each participant. Use the last row of the table to record sums. Answer the questions that follow and test the hypothesis that the male students at the university are different in physical attractiveness than males at other universities. Okay? So go ahead and take a look at this, right? So there's where we start. We start with the value of n, right here, the value of n. So n is the number of data points that you have in each condition, the number of subjects in each condition, and the number of n. In this case, it's 8, so you would write the number 8 right here. The degrees of freedom is n minus 1. If you can't remember that, you go to your handy-dandy formula, and there is the degrees of freedom right there, n minus 1 for the one-sample t-test. So n minus 1 in this problem is 8 minus 1, which is equal to 7. Now, use the space below to calculate the mean. So in order to calculate the mean, you go to your handy-dandy formula, and you know that mean is equal to sigma x over n. Okay, so we know n, which is 8. We know that. So now we need to figure out what sigma x is. Sigma x represents all the scores added together. Okay, so we go back to our little handy-dandy table, which I've represented here. And you take all the scores and add them together. All these scores here. Add them all together, so 9.4 plus 8.5 plus 7.7, all the way down to 8.8. And when you add them all together, you should end up with 66.1. Okay, 66.1. Now that we know sigma x and we know n, we can come over here to our problem and go ahead and write out the problem here. So what you're going to write out is you're going to say on your test, you're going to write x bar. Oops. You're going to write, let's see, you're going to write x bar equals sigma x over n. And then you're going to write, let's see, you're going to write 8.2, I'm sorry, you're going to write 66.1, which is sigma x, divided by 8, And when you crank that out on a calculator, you should get 8.26. Okay? So that is your mean, your x bar is equal to 8.26. Whoops, let me show that to you real quick. There you go. So that's what you should get there, and this is what you should write on the exam. Exactly this right here, with the different numbers, of course. Now, if we go back to our problem, now the next part D, is fill in the remainder of the table and compute sigma x minus x bar squared. So the purpose of the rest of this table, or actually the whole table, is to compute this number right here, sigma x minus x bar squared. So I've re-represented that table here on this spreadsheet. So here is the number. Here are the numbers. Whoops. Here are the numbers here. The data numbers. So what you're going to do on this table is right here, you're going to write the mean. You're just going to repeat the mean here. Okay, in the x bar column. Just write it down. And then you're going to take the score minus the mean and write that difference here. So in this example, 9.4 minus 8.26 is equal to 1.14. 8.5 minus 8.26 is equal to 0.24, etc., all the way down to 8.8 minus 8.26 is equal to 0.54. Okay, so take all those, take each one of these pairs and take the difference and write the difference here. Okay. Then after you do that, you're going to take this number here, the difference that you just calculated, and you're going to square it. So 1.14 squared is equal to 1.2996. 0.024 squared is equal to 0.0576, all the way down to 0.54 squared is equal to 0.2916. So you square all those numbers. And after you finish squaring all of those numbers, then you add them all together. So 1.2996 plus 0.0576 plus that, plus that, plus that, all the way down to plus 0.2916. And you should end up, when you add all those numbers together, with 7.8988. Or you could round that off to 7.9. Okay? And that completes this table. If you want to stop the video right now, make sure you have it correct. You may do so. But that's the whole purpose of this table, is to calculate this big long number here so that you can use it later on to calculate your standard deviation. So let's go back to the problem. We've calculated the sigma x minus x bar squared, so now we can go ahead and crank out our standard deviation. So let's go back to our sheet, and what we're going to write is, first of all, we're going to get the formula, which is right here, standard deviation. And we're going to write S. Oops, I want to use the pen. We're going to write S is equal to the square root of sigma x minus x bar squared divided by n minus 1. Okay, that's our formula. Now we've already done the hard part. We've already calculated sigma x minus x bar squared, right? We did that on our, here on the spreadsheet, but on the table. And that is 7.9, rounds off to 7.9. So you can say square root 7.9, right, which is that number right here, 7.89 rounded off, 7.9, divided by n minus 1, which is 8 minus 1, which is 7. Okay. Oops, let me go back to the table here. So don't forget, right, we already calculated that number, that 7.9. Right, we already did that number. It's that number right here. And then n minus 1 is 8 minus 1, which is 7. Okay. So that is going to end up being the if you do 7.9 divided by 7, you should get 1.13 rounded off. And then you take the square root of 1.13. Let's see. Oops. And you should get 1.06. Oops. Oh, damn it. Let me get rid of that real quick. Sorry about that. You should get 1.06 as your final answer. Okay? Final answer is 1.06. So that is the standard deviation of your sample. So the mean of your sample was 8.26, I believe. Yep, 8.26. The mean was 8.26, and the standard deviation is plus or minus 1.06. Okay. So now we know that. This is exactly what you'd write on the exam. This right here for your standard deviation. Let's go back to the problem. Now that we've done that for E, now we got to compute the standard error of the mean. Right. So we go over here to our handy dandy formula, and the standard error of the mean is very simple. Represented by capital S x bar is equal to lowercase s x bar divided by n. Okay, so standard deviation divided by the square root of n, I should say. So if we go back to our sheet, let's erase that. So we say the standard error of the mean is equal to the standard deviation divided by the square root of n. The standard deviation was equal to 1.06, I think. Square root of n, which is the square root of 8. Okay. And if you crank that out, 1.06 divided by the square root of 8, you should get 0.375. 0.375, okay? So 1.06 divided by the square root of 8 is 0.375. Okay, so that is your standard error of the mean, okay? And that is what you would put for number E. For F, that's the population mean, mu. So you go back to your problem. Right here. According to one paper, the average facial attractiveness of male college students in the U.S. as rated by females is 5.1. So mu is 5.1 in this problem. So the mu is equal to 5.1. Now the next is the dependent variable. The dependent variable is, of course, the name of the thing that we're manipulating, not the score, not the actual things we're counting, but the concept that we're manipulating. And if we go back up to the problem, we go and look to see the average facial attractiveness scores for each of the 8 target photos recorded below. So what we're counting here, or the thing that we're assessing, is facial attractiveness. Okay. Social psychologists wanted to test the hypothesis that the male students at her university are different in facial attractiveness than the students at other universities. That is our dependent variable, facial attractiveness. So you just write that here in this little column right here, in this little space right here. Squeeze it in there, facial attractiveness. Step 1 is the things that you're counting to assess facial attractiveness and the range. And you go back up to your problem. And the things that we're counting are right here in this table, and that would be mean facial attractiveness scores, or mean. The best answer would be average facial attractiveness scores or mean facial attractiveness scores, either one. You write that here, average facial attractiveness score. Range is from 1 to 10. Okay. Step 2 is where you tell me what that range means. You could say 1 to 3 is low facial attractiveness, 4 to 6 is moderate facial attractiveness, and 7 or greater is high facial attractiveness. Okay, something like that. Okay, something like that. Next is H. What is the alpha level? Again, you go to the problem, and the alpha level is the p-value, which is p less than 0.05. It's either going to be 0.5 or 0.1. So you write 0.05 here. Is the hypothesis of the experiment a directional one-tailed or non-directional two-tailed hypothesis? The way you determine that is by the language that's used to describe what the scientist is testing. So the social psychologist wanted to test the hypothesis that the male students at her university are different in facial attractiveness than students at other universities. And then in the last sentence here, we also have answer the questions that follow and test the hypothesis that male students at the university are different in physical attractiveness than males at other universities. Since we're only looking for a difference, in other words, the students could be uglier or the students could be hotter. It could go either way. Since we're looking just for a difference, it is a two-tailed hypothesis. Okay, it is a two-tailed hypothesis. So you would indicate here, you would circle, you would darken out the directional, the non-directional for two-tailed, right? If it was a directional hypothesis, it would say something like the social psychologist wanted to test the hypothesis that male students at her university are more attractive or less attractive in physical attractiveness, in facial attractiveness. Okay. So there would be a specific direction specified. But here we're just saying, are they different? So it's a two-tailed, non-directional hypothesis. Next is the statistical hypothesis. And this is where we indicate what the null hypothesis is and the alternative hypothesis is. These are the two hypotheses that we're testing. This entire process that you're doing on these problems is called hypothesis testing. That's what we're doing. We're doing hypothesis testing. And we're doing it to help decide which hypothesis to go with. In other words, to tell us specifically whether or not there are significant differences or there are not significant differences in the different things that we're measuring. So we're going to go back here to our little handy-dandy whiteboard. And as I taught you before, I always like to start off with writing out the the basics. And since you guys only know one test, you only know basically one type of hypothesis, and that's this one that we just learned. So what you're going to do is you're going to write your H sub 0 and your H sub A for your null hypothesis and your alternative hypothesis. And you're going to draw me a colon. And then the symbols that are being represented for the groups. In this case, it's X bar. And it's mu. So what we're testing, if you remember, right, we're basically testing our average of our sample of our 8 guys, which is represented by the X bar here, against the population that we got from some journal, which is, I believe, 5.1. So it's X bar versus mu. Okay, that's what we're comparing, and we're hypothesizing that there's no difference between them, or there is a difference between them. The null hypothesis says there's no difference, that they're the same, that they are equal. So this is a two-tailed hypothesis. So since it's a two-tailed, we use the equal sign to represent no difference between the mean of the sample that we gathered and mu. Okay, that's what the null hypothesis says. Null means nothing. There's nothing there. The opposite of the null hypothesis is the alternative hypothesis. The opposite of equal to is not equal to, so we use the not equal to symbol, which is a equal sign with a slash through it. So what we have here are the two hypotheses that we're going to put together, that we're going to combine, that we're going to test the head-to-head competition between the null hypothesis and the alternative hypothesis. And at the end of our process, we're going to be able to pick one of these guys. We're either going to pick the null hypothesis, we're going to fail to reject the null hypothesis, or we're going to reject the null hypothesis. And if we reject the null hypothesis, of course, if we reject that guy, that just leaves us with the alternative hypothesis. Okay? So that's what we're testing, we're testing there is a difference, there is not a difference. There is not a difference is represented by the null hypothesis. There is a difference is represented by the alternative hypothesis. Next, we go to K. Given the information you've identified about this study, which inferential test should be used for hypothesis testing? Which test should you use to to determine if it's the null hypothesis or the alternative hypothesis? Well, as I've said before, you only know one inferential test, and that is the one sample t-test. So you're going to write in this square right here, in this section right here, you're going to write one sample t-test, because that's the only one you know. Then for L is where we go ahead and calculate the one sample t-test, and that is to get a value that I call here t obtained. Okay. So if we go to our handy-dandy formula, it's right here. The one sample t-test is t is equal to x bar minus mu divided by the standard error of the mean, which is right there. Okay. So let's go back here. So t is equal to x bar minus mu divided by the standard error of the mean. Okay. So x bar that we got was 8.26. Mu was 5.1. And then the standard error of the mean was 0.375, I think. Okay. And you've got those numbers here in your problem, right? You've got the mean up here. You've got mu in the problem, right? That you wrote, and you wrote it down, right? You wrote down mu right here. You've got your standard error of the mean here that you calculated. And you've got your average, your mean, which you calculated here. Okay, so you've got all the numbers you need. You just pop them into the formula here, like so. And when we crank that out, crank it out for you real quick. You should get 8.43. Okay, 8.43. That is your number. And what I've scribbled here on this little whiteboard is what I expect to see on your test. You know, the formula, the numbers, and the answer. 8.43. So that's our obtained t value. Okay, yay, we got an obtained t. What does that mean? Well, we don't know yet because we've got to go to the next step. We've got to go to the table to use the provided table information recorded above to look up the critical value and record it here. So we go to our table, which I have here. And you need three pieces of information to use this table. You need the p-value. In this example, it's 0.05. You need to know if it's a one-tailed or two-tailed test. In our example, it's a two-tailed test. And you need to know the degrees of freedom. The degrees of freedom is n-1, which is 8-1, which is 7. Okay? So first you pick one-tailed or two-tailed. Right here, it's two-tailed. So we're going to use the second row of numbers here. Then you go to the alpha level, which is right here, 0.05. Could be 0.01 also on some problems, but in this problem it's 0.05. Then you go down and find the row that corresponds to the degrees of freedom, and it's right here. And the value that you get is 2.365. Okay, so what you're going to do is you're going to take that number, 2.365, and you're going to write it right here, 2.365. So now you have two numbers to compare. You have the value of t obtained, which is 8.43, and you have the value of t critical, which is 2.365. Now you compare the two and you make a decision. If the value of t obtained, if the value that you calculated from the data is bigger than the value that you get from the table, you reject the null hypothesis. If, on the other hand, this value that you calculated is equal to or smaller than the number you got from the table, you fail to reject the null hypothesis. Okay? So in this table here, in this problem here, the number 8.43 is bigger than the 2.365 number that we got from the table. Therefore, we reject the null hypothesis. So that null hypothesis that we wrote out before, is rejectable. We reject it, and that leaves us with the alternative hypothesis, which says that the mean of the sample that we gathered here in this little study is significantly different from the mean of the mu. So right here, what you're going to write is reject the null hypothesis right here. Now, what does that mean? Well, you go here to, and you got to tell me what that means based on the problem that you're presented. So I reject the null hypothesis. What does that mean practically? And what I expect to see here is a statement that uses the term significantly different and also talks about the averages that you compared, right? So what you would write would be something like, the average facial attractiveness score of the students in this study is significantly different from the population facial attractiveness score, right? Something like that, right? The average facial attractiveness score of the students that were in this study is significantly different than the population average facial attractive score. Okay? Something like that. Okay, I'm looking for a mention of the two means that you compared, the study facial attractiveness scores and the population facial attractiveness scores. Looking for the term significantly, and I'm looking for the term different or not different. If you fail to reject the null hypothesis, you either say there's no significant difference, right, between that and that. All right, that's it. I hope this helps.